All right, we're going to finish chapter 8 today. All right, first topic is ionization energies. When we're talking about ionization energies, we'll say we have sodium. All right, and so we want sodium to ionize into Na plus and 1 electron. All right, so when we're talking about an ionization energy, we're talking about how it will become a cation, right? And so this is very favorable. We have sodium, it's in the +1 column, and so this is a very favorable ionization reaction. All right, a very unfavorable ionization reaction would be, say, fluorine, who wants to be -1, not +1. And so your first ionization energy for your fluorine to the fluoride cation, this would be a very unfavorable ionization reaction. So when we're talking about ionization energies, we are normally focusing on the metals that form our cations. All right, and so this would be ionization energy number 1. All right, and so you can do it again. All right, and so if we do our electron configuration for sodium, sodium is number 11, and so that is 1s2, 2s2, 2p6, and then 3s1. All right, and so the reason why sodium is very stable as a +1 charge is that if we do this in terms of our noble gas, and that would be a neon, and then that is 10 of our electrons, and then a 3s1. All right, and so when we take out our electron, the 3s1, all right, that means now our sodium cation has the electron configuration of neon, which is a noble gas, and so that is a very stable electron configuration. And so now it is a 1s2, 2s2, 2p6 electron configuration, and that is very stable. It is the electron configuration of a noble gas. So that is a very stable electron configuration. All right, and so that is a very favorable ionization energy. Now we can do a second ionization energy, where we would take our Na+, which has a very stable electron configuration, and we try to take and remove another electron and get an Na +2 +1 electron. And so this would be ionization energy number 2. And so the ionization energy 1 makes it a +1. Ionization energy 2 makes it a +2. All right, and so you see that now we are taking an electron out of the noble gas core. That is a very unstable situation. And so this is a very high energy. All right, and so rule of thumb, it's about 10 times larger than the first ionization energy. And so it is 10 times the ionization energy of the first one. A normal would be it's double. So your ionization energy 1, ionization energy 2 would be twice that. When it goes up by a factor of 10, that is a large jump in energy. And that means that you are taking an electron out of your noble gas core. If we do the same thing with magnesium, all right, so magnesium goes to Mg plus and 1 electron. All right, so that is a relatively easy ionization energy to run. And so this is a low energy, ionization energy 1. That is a normal ionization energy. But note that this is neon. Magnesium is number 12. This is a neon with a 3s2. So now we are neon with a 3s1. All right, and so if we do ionization energy 2, that is a very favorable ionization energy. If we take our Mg, that is +1, and we take another electron out and get Mg +2, which is where Mg is in the periodic table, it's in column 2, very stable +2 ionization. All right, so this is a very favorable ionization energy 2. All right, and so a normal, again, ionization energy for the second one would be about 2 times your ionization energy of number 1. All right, so the large jump is going to come now, because now Mg+2 has the electron configuration of neon. If we try to take another electron out, ionization energy 3, that is going to be a very large jump in energy. And so if you take your Mg+2 and try to take another electron out and get Mg+3 plus 1 electron, that is ionization energy number 3. All right, and this is a very high energy. And so it is about 10 times the ionization energy of number 2. So again, that's a rule of thumb. It's about 10 times the previous ionization energy. So a normal change in ionization energy is multiplying it by 2. All right, and so a large jump is when it multiplies by, say, 10. All right, so then you have, if you see that you have a factor of about 10 of change in ionization energy, you know that you are pulling the electron out of the noble gas core. And that is a very high energy process. All right, and so there's going to be questions, say aluminum, and it will say you've got ionization energy 1, you got ionization energy 2, you got ionization energy 3, you got ionization energy 4, and it'll say which one has the largest jump in energy. All right, and so you have to see that aluminum on the periodic table wants to be aluminum +3. And so the first one is good, the second one is good, the third one is good. And so you can pull out the first 3 electrons without any trouble. You try to pull out that 4th electron, and this is going to be a large jump in energy. And so that would be a problem on the test. Where do you find the largest jump in energy when you're doing your ionizations of aluminum? And that would be when you go from ionization energy 3 to 4. Ionization energy 4 would be about 10 times that of the ionization energy of 3. That's the large jump in energy. And so here we'd multiply it by 2, here we'd multiply it by 2, here we'd have to multiply it by 10, because once you take 3 electrons out, the 4th electron is coming out of the noble gas core, and that takes a lot more energy. When they're talking about ionization energies here, we're talking about just the first ionization energy, but again, you need to know that there is a second, a third, and a 4th ionization energy. All right, so when you are looking at your pulling the electrons out of the various subshells, all right, so you'd pull it out of the S subshell versus the P subshell. All right, so when you look at the periodic trends for your ionization energy, all right, so you see that you have the lowest energies to get your ionizations to occur, all right, lowest energies, all right, that's your lithium, your sodium, your potassium, all right, so this is column 1, where all of these things want to be +1, all right, and so it's very easy to remove the electron from the first column. So they have the lowest ionization energy, the lowest amount of energy required to make that an ion. All right, and so then it, of course, goes up to the second. So in this case, beryllium, in this case, magnesium. So we did sodium, magnesium. All right, so sodium's first ionization energy is lower than the first ionization energy of magnesium. All right, so now we also did aluminum here. Now the first ionization energy of aluminum goes back down. And the reason for that is when you look at the electron configuration of neon, and then you got 3s2, and then you got a 3p1. All right, and so what you're doing here is you're pulling the electron out of the higher energy subshell, the P. All right, and so now you are left with a full S subshell. All right, and so that is easier to pull the electron that is spinning by itself in an orbital. All right, so it's up here by itself, easy to remove that one, versus the one we're moving for magnesium is neon 3s2. So that is a full subshell. And so you are taking the electron out that is a full subshell, and there is stability in a full subshell. And so it took more energy to pull that electron out. All right, and so then when you go to silicon, so again, every time, normally it goes up by, say, a factor of 2 each, but that's for the second ionization energy. All right, so these are just trends pulling out the first ionization energy. And so here you have the next one, all right, where it is silicon, all right, after aluminum is silicon. And so you have 2p, so you have a 3p2. So you pull this one out, it's relatively easy, but it didn't make anything more stable. You don't have a full subshell, half full subshell, right? So it just goes up as you would expect. Sulfur, same thing. It is a half full, and so taking one out is not that great because now it's not half full anymore. But note that when we go to the next one, and you have your the next, okay, so you got your going across, you got silicon, and then you got sulfur, and then you got your, oh, phosphorus was next. So that was phosphorus here. All right, when we do silicon, all right, so that one, these are very close together. So the P was the next one after silicon was the phosphorus, and then the sulfur. So when you look at sulfur, sulfur has a 3p4. All right, and so your sulfur being a 3p4, now you have a full first 3px. All right, and so we're going to take this electron out. Again, when you take this electron out, you have a half full p. And so that is why when you go to phosphorus and then down to sulfur, sulfur doesn't go up. It comes back down slightly, but it comes back down. All right, and so all of these that slightly come back down, nitrogen to oxygen, same thing. Nitrogen is a 2p3, and oxygen is a 2p4. So when you take this electron out of the the 3p4 or the 2p4, now you have a half full p, and so that is more stable, and so that ionization energy comes down. All right, and so then it just goes back up. So in general, you're just increasing ionization energy as you go to the right. There are a few things that are different. So ionization energy increases as you go to the right on your periodic table. The ones that go slightly down, all right, and that's when you have a, in this case, a 2p, well, a 2s2 and a 2p1. And so again, to pull out the P and make it an empty P subshell and a full S subshell, that is very stable. That's why that one goes down at that point. And then when you have your nitrogen to oxygen, your phosphorus to sulfur, again, you are taking a P4 and you take one of those electrons out, and now you have a half full P subshell, and that is more stable. But again, in general, your ionization energies increase as you go to the right. And note that the ionization energies, lithium is higher than sodium, sodium is higher than potassium, so it will decrease as you go down. So it is easier to remove an electron from cesium than it is lithium. All right, and so it decreases as it goes down, increases to the right, decreases down the periodic table. And then again, to the right, there's a couple of ones that do not increase, and that is when you get an empty P or a half full P. All right, so here is your ionization energies. In terms of a size of each sphere, indicates the size of the ionization energy. So in general, as you go to the right, it gets larger. All right, but you will see that when you go here to here, it gets smaller. Here to here, it gets smaller. Here to here, it gets smaller. Again, this is a P4, and when you take a P4 and make it a P3, now it is half full. When you go from here to here, it is getting smaller. So these are the ones that are not in the trend of increasing going to the right. Again, this is an S2. This is a P1. When you remove the P1, now you have an empty P subshell. And there is stability in an empty P subshell. and that's why it's easier to remove this P than it is to remove the S2. All right. So here is your dramatic increase. Again, what I call dramatic increase is, again, a rule of thumb. It is about 10 times the previous ionization energy. All right. And so when that occurs is when the first electron from the noble gas core is removed. So we did those examples. The ionization energy 2, 3, 4, they always increase, but 1 is going to go up, not by a factor of 2, but a much larger factor. So I like to, in general, it's a factor of 2 versus a factor of 10. But you will see a much larger increase in energy. And so they will just call it a dramatic increase in energy. All right, so here are the different elements. Which one? Well, we didn't do any of these. Okay, fine. All right, so your element hydrogen, first ionization energy. There isn't a second because hydrogen has 1 proton, 1 electron. We can only remove 1 electron. There is only 1. Helium has 2 electrons. You can remove 1, and note the second one is approximately times 2 because this is removing a 1s2. This is removing the 1s1. They're both in the same subshell. All right, so lithium. All right, so we have the first one. All right, and so again, this is not times 10, but anyway, if it was 5,000, it's more than times 10. But anyway, it's a dramatic increase in ionization energy going from 520 to 7,298. All right, so that is your dramatic increase because lithium is 1s2, 2s1. So you can remove the first one. That is very easy. It is very difficult to remove the second one because that is the electron configuration of helium. And so that is your dramatic increase. Although 11,800 is larger than 7,000, but again, the normal change in your ionization energy is about multiplying by 2. Again, it's off by a decent factor. Again, rule of thumb, about a multiplication of 2. All right, so beryllium, that is a 2s2. So the first one comes out. The second one, note, it's about a times 2. That is a normal increase for the second ionization energy. And then here is a dramatic increase, a large increase, about times 10. Okay, times 10 would be 17,000. This one is only 15,000, whatever. All right, but again, approximately about times 10. And this one is a normal increase. All right, so that is about times 2. It's much less than times 2. It's 1.5. It's not 28, it's 21. All right. So boron, that has your 2s2 and your 2p1. And so the first one, all right, and this one's more like multiplied by 3 instead of 2. All right, and then the next one is multiplied by less than 2. And then here is where you have your dramatic increase. It's not quite multiplied by 10, but you're going from 3,000 to 25,000. All right, so it is a large increase, factor of 7 or so. And then here again, less than a factor of 2. Carbon, 2s2, 2p2. All right, so multiply it by about 2, by about 2, by about 2. And now you're going to multiply it. Well, here is more like 6, but anyway, it is much larger than your factor of 2. So in this case, if you divide it, this is more like a factor of 6. When you divide these, more like a factor of 7. All right, so it's not 10. 10 is just an easy number to remember. It is a factor larger than 5. All right. All right, so here again, multiply it by 2, multiply it by 2, multiply it by 2, multiply it much less than 2. And then here is a multiplication of about, say, 6. Again, 5 or 6 there. Here, this is more like times 3, but times 2 here, less than times 2 here, less than times 2 here, less than times 2 here. And now you're going from 13 to 71. So that's again times 5 or 6. Okay, so whatever you divide those, and so again a large increase, and that each time is when you're taking the electron out of the noble gas core. That's when you get a large increase in energy. But note, after that, like here, you took one out, it went from 520 to 7,298. The next one takes 11,815. It is always going to be more for the next ionization. All right, you're looking for the factor increase by a factor of whatever, more than 5 is the dramatic increase. All right, so if we look at the periodic table, all right, and so again, when you are, if you remember, this is an increase in your ionization, and this is a decrease in your ionization, and so this one would be the lowest, and this one would be the highest. All right, so you have to know your periodic trends for your ionization energy. And so when it says to arrange the elements in order of increasing, and so that means you're going to list the SB first, then the AS second, and then the BR third. That would be in order of increasing ionization energies. All right, so that's ionization energies. The other reaction that we're looking at that makes ions is electron affinity. But this time we're going to make an anion. So this time we're going to take, say, sodium, and we're going to add an electron and make it a sodium minus. All right, so that is a very unfavorable reaction. Sodium does not want to be minus. Sodium wants to be positive. So that is very unfavorable. But now, unlike the last time when F was unfavorable, F plus 1 electron, now that is very favorable. When you have your periodic table, you have your halogens, and they all want to be -1. F is in the -1 column. There's a reason why F is in the -1 column. So fluorine has the electron configuration of 1s2, 2s2, 2p5. All right, so it is number 9. And so there are the 9 electrons for the electron configuration of your fluorine. All right, now we're going to add an electron. And so now we have a negative charge. Now that means, again, we still have 9 protons, but now we have 10 electrons. And so the electron configuration, we have to put in another electron. And that is 1s2, 2s2, 2p6. This is the electron configuration of neon. This is very stable. All right, and so we will have a very favorable electron affinity for fluorine because that gives it the electron configuration of a noble gas. All right, and it is so favorable, it is actually exothermic because that makes a very stable anion. All right. So many of your metals do not have an electron affinity. They just will not become negative. All right, and so you have your anion valence. So note here, group 2A and group 7A do not form stable anions. All right, and so note here that 2A is not listed, and 8A is not listed, okay? All right, so this is your second column, so that's your alkaline earth metals, and then this is your noble gases. They will not form stable anions. All right, so you can get your sodium to form a stable anion. It is not favorable, but it will form. You cannot get them to form for column 2. All right, column 3, you can form them. Column 4, you can form them. And column 5, you can form them. But they are not very stable. But now, when we get to our oxygen column and our fluorine column, now we have, oxygen wants to be -2, and your fluorine wants to be -1, the fluoride ion. And so those make very stable anions, and so they are more exothermic in their electron affinities. All right, so when you try to draw a trend to see what trend you get, it's kind of all over the place. The key is here that your halogens have a very exothermic electron affinity. All of these are very stable as anions. All right. That's about it. The other ones are not very stable when they form their anions. The next ones would be, say, your oxygen, sulfur. All right, so those are the, so this is your halogens, that's group 7. Your group 6s are here. And then the other ones are not very stable, and some do not, well, the ones that are 0, they cannot form a stable anion. All right, so here's your electron affinities. You will not need to know these numbers. All right, so again, 8A, they do not do electron affinities. Group 2A, they do not do anions. They do not do electron affinities. All right, so you can get them done with column 1, column 3, column 4, not for 1 here in column 5, but column 6 and 7. So these are the ones that have very favorable exothermic electron affinities. The rest of them do not want to become anions. And so obviously you have the much larger exothermic numbers when you have your group 7, which is your halides, which are in the -1 column. They want to have the electron configuration of the noble gas. So they are very favorable to gain 1 electron. All right. All right, so when you have a here dramatic difference in ionization energies, all right, when you hear ionization energies, you have to think cation. So ionization energies, cations, electron affinities, you have to think anions. All right, and so when you have a dramatic difference in ionization energies at the 3rd ionization, that means it's easy for ionization energy 1, easy for ionization energy 2, ionization energy 3 has a big jump. All right, so that means that you are taking it out of the noble gas core once you hit the 3rd one. All right, and that means you are a group 2A element. First electron comes out, fine. Second electron comes out, fine. Now you have the electron configuration of the noble gas. The 3rd one is going to have a dramatic increase in ionization energy. All right. Elements with low ionization energies tend to be metals. Those with the high ionization energy tend to be nonmetals. All right, so again, metals are easily ionized. Nonmetals, they want to be more anions, not cations. All right. So now we're going to take and we're going to burn our metals. So what we did in lab, we took magnesium, solid, and we burned it. And we made magnesium oxide. All right, and so when we balance that, we have a 2 here and a 2 here. So this is a metal oxide. All right, so a metal oxide is going to be basic. And so if you hear the term basic oxide, that means that you have a metal oxide. All right, and so when we burn magnesium, we made a metal oxide. Now, it is a basic oxide because when you add water, you form a base. So when you take your magnesium oxide and you add water, you get magnesium hydroxide, a base. All right, and that is balanced. All right, so a basic oxide, if you have a metal oxide, that is a basic oxide, which means you take that metal oxide and you dissolve it in water, you're going to form a base, a metal hydroxide base. All right, if you are an acidic oxide, then you're going to be a non-metal oxide. All right, so if we take carbon and we burn it, we get carbon dioxide. When we take carbon dioxide and we add water to that, we get carbonic acid. All right, and so again, when you're releasing CO2, anytime you're burning anything, you release CO2, burning anything organic. All right, and so then when it rains, the water goes through the carbon dioxide and you get some carbonic acid, you get acid rain. All right, so anytime you have a metal oxide and you add water, it is going to be basic. Anytime you have a non-metal oxide, carbon dioxide, you add water, it's going to be an acid. All right, you can also have some amphoteric oxides which react with both acids and bases. All right, so there are the zinc hydroxide is the most famous of those. You can have ZnOH sub 2, and so your zinc hydroxide can react. It's not an oxide, it's a hydroxide, but it reacts with both acids and bases for your amphoteric. But normally your amphoteric oxides, when you're not a metal or a non-metal, you're looking at a metalloid. So your metalloid is, say, boron. So you can have boron. Boron is in the +3 column, and so if it makes an oxide with an oxygen that is -2, you've got a B2O3. All right, so now you have a metalloid oxide. And so when you add water to that, you can get the acid, which would be HbO2. Now, when you do these, note the oxidation numbers, all right? So, of course, when you're burning it, that is an oxidation. So magnesium here starts at 0, and now it is +2. So we have oxidized the magnesium. Now, when we're just adding water, this is not an oxidation reduction. All right, so when you're adding water, your +2 oxidation will remain a +2 oxidation. Here, carbon, solid, graphite, 0, carbon dioxide, +4. All right, and so your +4 carbon in carbon dioxide has to be a +4 over here in your acid. And it is because oxygen's -2, so that's -6. Hydrogen's +1, so that's +2. +2, +4, -6. Carbonic acid is neutral. All right, and so when you burn your boron, boron plus oxygen to get your B2O3, that is an oxidation. Boron is 0. Now boron is a +3. So now when your boron's a +3 and you make an acid, now you have to make sure that your boron remains a +3. And so you have a +1 hydrogen, and you've got 2 oxygens, and now you have a +3 boron. But note, it is a metalloid oxide, so the B2O3 can react with water to form the hydroxide. And so since we know that B is going to be +3, we know that that is BOH sub 3 because we know that hydroxide is -1. And so to balance that, we would need 2 here, and then we would have 3 here, and we have a balanced reaction. All right, so if you are a metal oxide, you add water, you get the hydroxide, you get the base. When you have a non-metal oxide and you add the water, you're going to get an acid. All right, and the 2 most stable acids, we're going to do the ic acid and we're going to do the us acid. All right, and so we do know that carbon burns an oxygen to give CO2. We also know that it burns and gives carbon monoxide, and that's why we have carbon monoxide detectors. We don't want that. That is very poisonous, but we do know that carbon also burns with oxygen to give carbon monoxide. And so to balance that, you have a 2 there and a 2 there. Now your carbon oxidation is +2. So when you add water to carbon monoxide, you add carbon monoxide plus H2O. you get H2CO2. So this is carbonic acid, and the ic acid is the most stable acid, and then you got the carbonous acid. All right, and so when you burn oxygen, you get mostly CO2, but you will get some CO. All right, and so you always will know what you're going to get when you have your nonmetals. You're going to get your ic acid, you're going to get your us acid. So you have to remember all the different acids that were the ic acids and the us acids. Because if we are going to go burn some, what do we want to burn? Sulfur. Let's burn some sulfur. All right. So now you wouldn't know what the product is unless you know that I know it's going to make the ic acid. I know it's going to make the us acid when I add my water. All right. And so let's look at our sulfur. So S8 plus O2. What is that going to give? All right. What we do know is that whatever it gives, when we add water to that, we're going to get sulfuric acid, H2SO4. Then we do the same thing again because we know we're going to get the ic acid. We also know we're going to get the us acid. So the S8 is going to react with oxygen. And when we add the water to that, we are also going to get the H2SO3. So here is sulfuric acid. And here is sulfurous acid. All right, and so we get the ic acid and we get the us acid. So we have to know how to do our oxidation numbers. So we already did this. We know that oxygen is -2. This is a -8. We know that hydrogen is +1, so this is a +2. And so we see here that we have a +6 oxidation for our sulfur. And so we know that when we have our sulfur oxide, that the sulfur is going to be +6. We also know that oxygen is in the -2 column. And so to get a neutral oxide, we have SO3. And then to balance that, since it's S8 in octamer, we need 8 of these. That means we have 24 oxygens, so we have 12 O2s to balance that. And so when we have our SO3 here, and we add H2O, we get H2SO4, and that is a balanced chemical reaction where the +6 sulfur, again, when you're adding water, you're not changing. That is not an oxidation reduction. And so your oxidation of sulfur +6 is then the same +6 in the sulfuric acid. Same thing over here, sulfurous acid. Now we only have 3 oxygens, so that's -6. We still have our 2 hydrogens, that's +2. So this time our sulfur is +4. In order to get a +4 sulfur, we need SO2, where your oxygen is -2, that's -4, sulfur is +4. Your oxides are all neutral. All right, and so you have, to balance this, you need 8 SO2s, and that would then require 8 O2s to balance that. And you have your SO2 plus H2O gives H2SO3. Your +4 sulfur is still a +4 sulfur. All right. All right, so let's go to the 1A, alkali metals. Let's look at sodium. All right, so we're going to take sodium, and we're going to add oxygen. All right, and so we're going to get sodium oxide, and that is Na2O. How do we know that? Well, sodium's in the +1 column. And so oxygen's in the -2 column. And so it is the Na2O. And that's what they're showing here. Any of the metals that you use in column 1 is going to give you a 2 of those metals to 1 oxygen ratio. All right, to balance that, we need a 2 here and a 4 here. All right, again, when we add water to this, Na2O, this is a metal oxide, and when you add water to a metal oxide, you get a base. And so when you add water to this, you are going to get NaOH. And to balance that, you need a 2 out in front. So the metal oxides in water are going to give you a base. When we go to column 2, now we have let's say, well, we already did the magnesium. We already did this one. So magnesium plus oxygen gave magnesium oxide. To here, to there. And so that's why the formula for column 2 is going to be the metal with oxygen. The metal with oxygen. Again, you take that and you add water. When you have a metal oxide with water, it's going to form a base, MgOH sub 2. So we did the group 2 already with our magnesium. Group 3, right? Okay, so boron is actually acidic, but you would not need to know that. You do need to know that that is a metalloid, and so we're going to predict metalloids to be amphoteric. All right, so unless I tell you otherwise, metalloids are going to be amphoteric, where your aluminum is not a metalloid. Aluminum is a metal, but it is amphoteric, which means it will make an acid or a base with that oxide. All right, so when we take our group 3 oxides are basic, okay. So once you're down, you go down, you have all metals. So boron, they're saying, is going to act as a non-metal. Aluminum is going to act as a metalloid and be amphoteric. So when you're doing this, all of them on the test, the non-metals are going to be acidic, the metals are going to be basic, and the metalloids are going to be amphoteric, which means they can be acidic and they can be basic. All right, so we did the boron one for this already. When you go to carbon, we already did carbon. All right, so note that this group is very diverse. You start with carbon, which is a non-metal, and then you go down to the bottom, and now you've got tin, and you got lead. All right, so you've got metals. All right, so you have both non-metals, your carbon, your silicon's a metalloid, and then you go down further, and now you have your metals. Again, for anything on the test, if it is a non-metal, it is going to be acidic. If it is a metal, it is going to be basic. So if we do tin and we burn tin, you have to know from previous tests that tin will come as a +2 and tin will come as a +4. And so you're going to have 2 oxides for this metal because you memorize that tin has 2 stable oxidations. So you're going to have SNO, and you're also going to have SNO2. Because here it is +2, and here it is +4. And tin is, of course, a metal. And so for our test, we're always going to have the metal oxides be basic. And so the SNO plus H2O is going to give our SNOH sub 2. And our SNO2 plus H2O is going to give us our SNOH sub 4. All right, and so again, we have tin that is +2, we have tin that is +4. To balance this, we need a 2 in front of this water. All right, so when you burn your metals, tin is one we have memorized. We have it as a +2 and a +4. You will have to know that. Your iron, when we burn iron, iron comes +2, iron comes +3. You're going to get 2 oxides when you burn iron. Copper is +1, copper is +2. You're going to get 2 oxides when you burn copper. And then all of the metals are then going to react with water, the metal oxides, and this would be FeOH2. This is going to be FeOH3. This is going to be CuOH. This is going to be CuOH2. You're going to get the metal oxides that are going to be dissolved in water to make the base. All right, so here's some oxides. We made our magnesium oxide. That was a whitish gray solid. All right, so now we have to know our nitrogen and phosphorus. So we have to remember our nitric acid, HNO3, and that means our nitrous acid is HNO2. The only way you can know what is the oxide going to be when I burn my nitrogen, so nitrogen plus oxygen, what are you going to get? If you do not know the nitric acid and the nitrous acid, you are not going to be able to predict the stable oxides. All right, so when you have your HNO3, you got a -6 for the 3 O's, you got a +1 for the H. So you got a nitrogen that is +5, +5, and you got a oxygen that's going to be a -2, and you have to form a neutral oxide with nitrogen. And so the common factor between a 5 and a 2 is, the common multiple is a 10. And so you're going to have N2O5 for a -10 and a +10. So nitrogen, 2 of them is +10. So each nitrogen here is a +5. All right, and so to balance that, we need 2 here, we need 5 here, we need 2 here. So we have our N2O5, and when we take our N2O5 and we add H2O, that's when we get our nitric acid, HNO3. All right, and so to balance that, we need a 2 right there, and that does it. That balances it. So again, our nitrogen here is +5. When you add water, that is not going to change the oxidation number. This is not oxidation reduction. It's simply dissolving it in water, and you have then a +5 oxidation that remains for your nitric acid. All right, and so there is your N2O5. That's this one right there. All right, so again, when you have your nitrous acid, you have your -4, you got your +1, nitrogen is +3. And so for your nitrous acid, we have a nitrogen that's +3 with an oxygen that's -2. Your least common multiple is a 6. And so when you take your N2 plus your O2, you're going to get an N2 for the +6 and an O3 for the -6. And to balance that, we got a 2 here, a 2 here, and a 3 here. Again, here's your N2O3. Here is your N2O3. All right, so when we add water to N2O3 plus H2O, that's when we get our nitrous acid, HNO2, and we will need 2 of those. Again, here is your +3, and here is your +3. When you add water, you're not changing your oxidation numbers. Right? So that would work exactly the same for your phosphorus, because when you do phosphorus, your phosphoric acid is H3PO4. Again, you got your -8, you got your +3, +5. Anytime you have a +5 oxidation and you're going to make an oxide, that's when you get, in this case, your P2O5. You're going to get P2O5. All right, if you have your nitrous acid, H3PO3, you got your -6, your +3. Again, you got a +3. That's going to give you your P2O3. So for every group 5, you're going to end up with a, whatever the element is to, O3, whatever the element is, whether it's nitrogen, phosphorus, and then 2 of those, and then O5. All right. All right, so we're not going to burn oxygen, but we are going to burn sulfur. So to have OO2 and OO3 would make no sense. So we do not burn oxygen. We burn sulfur, selenium. All right, so we have, we already did the sulfur. And so we had the SO2 and we had the SO3. And when we added water to that, we got H2SO3 and we got H2SO4. Sulfuric acid, sulfurous acid. And so that is going to be the same for your group 6 elements. All right, group 7. All right, so you have to know your chloric acid and your chlorous acid. HClO3 and then HClO2. That is your chloric acid. And this is your chlorous acid. All right, so again, you need your oxidation numbers. You got your -6, you got your +1, you got your +5. And so the Cl is +5, your oxygen is -2, and so you have a Cl2O5. All right, and then you'll have your +3 here, and so you're going to have your Cl that's +3 and your O that is -2, and so you're going to have your Cl2O3. And when you add water to this, you're going to get, so you add water to this, that's when you get your chloric acid. You add water to this is where you get your chlorous acid. All right, and so the balanced reaction is chlorine gas plus oxygen gas is going to give Cl2O5. And to balance that, we need 2 here, 5 here, and 2 there. And then you take your Cl2O5 and you add H2O, you get HClO3. And you need to balance that with a 2. You will also have your Cl2 plus O2 giving your Cl2O3. To balance that, we need 2 here, 2 there, 3 there, and then your Cl2O3 plus H2O is going to give you your chlorous acid, HClO2. And to balance that, we need a 2 there. And then the noble gases, they are not going to be reactive, so they will react in other chapters, but we're not able to burn our noble gases. All right, so you have a metalloid, R2O5, identify the element. All right, so again, you are in group 5A when you have this formula. All right, and so you're going to have a multiple choice. So you will have either your AS or your SB for your answer. And so the oxide is acidic, so it's going to be arsenic. Yeah, that's not, I would not put that question on the test. Metalloids would be on the test, amphoteric. And so they would be both acidic and basic. All right, so that is the end of chapter 8. We're going to do some more for a periodic table, one with the elements listed. It's going to be this right there. All right. So a big part of the test is going to be electron configurations and quantum numbers, but also ground state versus excited state versus forbidden state. All right, so on the test, I may have hydrogen, and then I would say 1s1. And the question is going to be, what is the charge? Is this a neutral hydrogen? All right, so you're going to be given the question, give the charge. All right, and then it's either going to be whatever, positive, negative, neutral. Give the charge, and then state whether this is the ground state. There is only one ground state, but there's one ground state for the cation. There's one ground state for the anion. There's one ground state for neutral. And then there's a million, billion, infinite number of excited states. And there is an infinite number of wrong answers completely called forbidden states. All right, so you're going to be choosing between ground state, excited state, or forbidden. So when the question is hydrogen, 1s1, well, hydrogen should have 1 electron, and so this one is neutral. And if I said to give the electron configuration of hydrogen, you would write 1s1. That means it is the ground state. If I have hydrogen and I write 2s1, you would write, well, this has 1 electron. It is still neutral. It is not the ground state. There is only one neutral ground state, and that is hydrogen 1s1. And so this one would be an excited state because the 2s1 does exist. If I have hydrogen and then I write 1p1, well, it's one electron, so it is neutral, except there's no such thing as a 1p. The p starts at 2, and so this is forbidden. All right, so when you put a electron in a place that doesn't exist, then that is forbidden. If you put more electrons than will fit in a subshell, that is forbidden. All right, so if I say hydrogen and then I write 1s2, if I had hydrogen and a 1s2, now I have 2 electrons. That means I am an anion. Or you could write -1. So that would be a hydrogen that is -1. And if we added an electron to the hydrogen, that is where we would put it. This is the ground state. Again, the ion is going to have a ground state. The neutral is going to have a ground state. All right, if I write hydrogen and I write 1s1 and then I write 4f1, all right, so now I see that I have 2 electrons in my hydrogen. It's only supposed to have 1 electron. So again, this is an anion. It is a -1 charge. All right, so the ground state would be a 1s2. This is not the ground state. The 4f does exist. So the S starts at 1, the P starts at 2, the D starts at 3, the F starts at 4. So that does exist. And so this is simply an excited state. All right, and if I wrote hydrogen and then I wrote a 3f2, well, you would say, well, there's 2 electrons, and so it's an anion, -1 charge, but F starts at 4. There's no such thing as a 3f, and this would be forbidden. All right, and so you will have, again, let's do making cations. So when you make a cation, so it is a different rule for making a cation. So when you do the anions, you simply add the electrons just like the buildup rule. Unfortunately, when you're doing cations, you do not go reverse of your buildup rule. All right, so to form a cation, let's do, which one do we want to do? Let's do, let's do zinc. All right, so we're going to do the electron configuration of zinc. So zinc, I'm going to use the first prior noble gas, argon. So I have argon. And then after argon comes 19. 19 is potassium here, starting the 4s. So the 4s2, 1, 2. And then I come to my first D, and I know that that is a 3D. And then I have to go all the way across to 10 of them, 3D10. All right, so when I do zinc, it is argon 4s2 3d10. All right, so argon, so zinc, argon 4s2 3d10. Now, this is the ground state electron configuration of neutral zinc. All right, so now I know that zinc is a very stable +2 ion. So now I want zinc +2, which means I have to remove 2 electrons. All right, and so on the test, anytime you see an answer on the homework, you will never see the answer written this way. The answer, it is acceptable to write it this way. I hope it should be. I will accept that as the right answer. But you are to write it in number order. And so a better answer, the same answer, but better, is a 3d10 4s2. All right, you write it in number order, 3, then 4. All right, the buildup chart puts it in this way. When you give your final answer, you should put it in number order. There is a reason for this. because when you take electrons out, you do not go this way. You do go this way. All right, and so you take the electrons out of the highest N energy level. So when you have a 3 and you have a 4, you're taking electrons out of the 4s. That is not how it was put in. It was put in the 4s2 first, then it went to the 3d and put them in. When you remove electrons, you take them out of the highest N energy level. And so your zinc plus 2 is an argon 3d10. So it doesn't matter if you write it this way or if you write it this way, but when you have the zinc plus 2, there is only one answer, and that is a 3d10 after your argon noble gas core. If you give, okay, so this, and this is a good question, then I would have this as a question, zinc plus 2, and that's argon. All right, and then I would have a 4s2 3d8. So this is the ground state, cation. So this is a zinc plus 2 ground state. All right, this is also a zinc plus 2. All right, but we took the electrons out of the wrong subshell. So that is not the ground state. This is an excited state. All right, because all these things exist. Is there a 3D? Yes. Can we fit 8 electrons in there? Yes. Is there a 4s? Yes. Can we fit 2 electrons in there? Yes. All right, if I had a zinc plus 2 here, and I said it was an argon, and then it was a 4s5 3d5, trying to half fill my D subshell. All right, so this would be a zinc plus 2. It's still the same number of electrons, 28, 28, 28. All right, so it's still a zinc plus 2, except you can't fit 5 electrons in a 4s. You have a maximum of 2 electrons that would fit in the 4s subshell, and so that is forbidden. You cannot fit more than 2 electrons in an S subshell. When you put 5 of them in there, that is forbidden. All right, and so you'll have questions just like this. It'll be written zinc plus 2, and it'll have the ground state, or it'll have an excited state, or it'll have a forbidden state. All right, so you have to remember when you are doing cations, you take them out of the highest N energy level. Again, I don't care if you write it 4s2 3d10, but you have to know that when you remove it, you're removing it out of the 4s2. And that's the reason why they prefer you to write it in number order. All right, not the order that it is put in. And so then if you need to take one out, maybe you'll remember that you're taking it out from the highest N energy level that is listed at the end if you properly rewrite your electron configuration. These answers to me are exactly the same. But if you can't do this right, maybe you should put it this way, and maybe you'll remember that's the reason why I put it that way. When I take them out, I have to take them out of the highest N energy level, which will now be on the right when I rewrite it. All right. Let's do uranium, which is number 92, and let's do uranium 92. That is a plus charge. All right, so we're going to go back to our periodic table, find uranium, which is number 92. All right, oh, it's not on our periodic table. Great. All right, so here is 87, here is 88. And down here is 89, 90, 91, and 92. This is uranium, number 92. All right, and so, and then there is a group right above it. Let's see, we got 56. So we got 57, 58, 59, blah, 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 and we got more things over here. All right, so we are at 92, uranium, right here. So the first prior noble gas, Rn, 86. And so we would write Rn that will take up 86 of our 92 electrons that we need for uranium. All right, and so then in period 7 comes the 87 and 88, and so that means we have a 7s2. Now we're at 88. Then we come down here to the bottom where you have your 4f here, and now your 5f below that here. And so here is the 5f, and we have to count over 1, 2, 3, 4. And so then we have a 5f4. And so when you add it up, 86 plus 2 plus 4, you have a 92 for uranium. All right, 7s2, 5f4. All right, so here is your electron configuration of uranium. All right, so now you have uranium plus, and then we could also have uranium minus. All right, so minus is much easier. So you have Rn, and then you have 7s2. We just add an electron, 5f5. All right, and so the plus charge is missed quite a bit because, again, people write it this way, and then they just take an electron out. But you have to know the rule. When you take an electron out, it must be taken out of the highest N energy level. And 7 is much higher than 5. And so this is a 7s1, 5f4. Again, the answer is going to say Rn is it's going to be uranium is Rn, and then a 5f4, 7s2, because they will put them always in number order in your answers. All right, and so then maybe you'll remember that you are taking it out of the one on the far right, and that would be a 5f4, 7s1. All right, and so here, if you had Rn and you say, oh, I'm going to add one, and then you say it is a 5f4, 7s3, all right, which would be a question on the test, and that would be then, of course, forbidden. You cannot have more than 2 electrons in any of the s orbitals. All right, so when you write it correctly and you're doing an anion, just don't stick it on the last one, because many times that is going to be wrong and forbidden. All right, so like every time that you are an F or a D, it's going to be wrong and forbidden, because that's going to have an S at the end. All right, so you would have to then, of course, have it as a 5f5, 7s2 for the ground state. So you will have a ground state anion, you will have a ground state cation, and you will have a ground state neutral. And then when I ask a question like uranium, and I have Rn, and I have 5f6. All right, so what is your answer for uranium given the electron configuration Rn and then a 5f6? Looking for an answer.